Hi, good day. So this discussion is for the elementary applications of differential equation. So let's have the growth and decay. So let us assume n as the amount of substance or the number of population that is either growing or decaying. So for our equation, that is the differential n, or the change in population with respect to time, is directly proportional to the number of population itself. So let us have an equation. So for us to have the equation, this is differential n with respect to the change in time is equal to, so from proportionality to an equation, we are to place a constant times n, wherein this k is simply, the proportionality constant. Alright, so let us solve for the solution of this equation. So we are to bring this n on the left side of the equation. That will be a denominator. So dn over n will now be equal to, so that is the constant k times differential time. So we are now to integrate both sides of the equation. So what is the integral of dn over n? So that is simply the natural logarithm of n is equal to, so this is k, the constant. What is the integral of dt? That is simply t, plus the arbitrary constant c. So we are now to simplify our solution. So to remove this natural logarithm, we are to use this is now e raised to ln of n is now equal to this is e raised to k times t plus the arbitrary constant c. So if you are to recall the basic for natural logarithm, basically, for example, that is e raised to ln of x is simply equal to x, since the base of natural logarithm is also e. So we are to cancel that. So e raised to ln of x is simply x. So for this case, e raised to ln of n is simply equal to n. And this is now equal to, we are adding exponents, or we have an additional operation for the exponents. So if we are to separate these two exponents, we can have, that is e raised to k times t multiplied by e raised to c. So take note that if we have this value e raised to c, e raised to constant is the same as constant, or simply constant. So we now simplify our equation. That is, now we have n, or the number of population, is simply equal to this constant c multiplied by e raised to k times t. So in general, so for the function of the population with respect in terms of time is now equal to c e raised to k times t. So this equation is applicable for the growth and decay. So one application, elementary application for differential equation. So let's have an example. Okay, so let's have this first example. So a person places 20,000 pesos in a savings account which pays 5% interest per annum, compounded continuously. So find letter A, the amount in the account after 3 years, and letter B, the time required for the account to be double in value, presuming no withdrawals and no additional deposits. So let's have the given. So let's have this as at time is equal to 0. Okay, so what is the initial amount of the savings? So the initial amount, n, we are to use that value, the given. This is the 20,000 pesos. So these are our initial values. Then we have this given, the 5% interest per year. So that is our constant k, the constant rate of the deposit. So this is 5% k, or that is, let's say, 0.05. So basically, since this is a deposit, we are expecting that the value will grow. So we have to use our previous equation, that is the n as a function of time is now equal to c times e raised to k times t. So first, we need to compute for the value of the constant. So what is the value, again, at n at time is equal to 0? What is the value of n at time is equal to 0? That is our initial value, or the 20,000 pesos. So we are now to substitute. So this is 20,000 pesos. This is 20,000 pesos is equal to the constant. This is E, our rate, that is 0.05, or our proportionality constant, raised to our initial value at time equal to 0. But basically, if we have a value raised to 0, since that is 0.05 times 0 is 0, any value raised to 0 is the same as 1. So we can have now the value of the constant as C is simply equal to 20,000 pesos. Okay, so then we can now solve for question letter. Okay, for the first question, that is letter A. What is the amount in the account after 3 years? So let's have the value of T, that is at T is equal to 3 years. So we have to do is substitute, that is at n of t is now equal to c e raised to the k times t. So this is what is the value of the savings, or the amount of the savings at n of 3 is equal to c, that is equal to 20,000. This is e raised to, the rate is 0.05 multiplied by 3. So this will be the amount of money in that savings after 3 years. So this is 20,000 multiplied by e raised to 0.05 multiplied by 3 years. So let's have that as 23,236.685. 23,236. 236.685 pesos. So this will be the amount of the money in that savings after 3 years. So this will be our solution for letter A, or for the first question. Okay, for the second question, letter B. So we are required to compute for the time required for the account to double in value, presuming no withdrawals and no additional deposits. So we are just to double the value. This is for letter B. So what is our initial amount? That is 20,000 multiplied by 2. So expected value will be equal to 40,000. So if the money is now at 40,000, we are looking for the time in years. So we have our equation again, that is n of t is equal to the value of c e raised to the k times t. So all we have to do is substitute. So this time we are using the value of n, or the amount of money in that savings, as 40,000. So this is now 40,000 is equal to the constant. You are able to compute that a while ago. That is 20,000. This is now e raised to 0.05 multiplied by the time. So we may divide both sides of the equation by 20,000 to simplify. So basically, 40,000 divided by 20,000 is equal to 2. And it's now equal to e raised to 0.05 t. So all we have to do is bring down that exponent to solve for the value of t. We are using natural logarithm. ln of 2 is now equal to the ln of e raised to 0.05 times the time. So we may now bring down this exponents. So we have the ln of 2. The ln of 2 is now equal to the 0.05 of the time, or the ln of e. But basically, we know this value, ln of e is the same as 1. So computing for the time, We may divide both sides of the equation by 0.05. So the time, this is now in terms of years, is now equal to, this is the same as the ln of 2, divided by this is ln of 2 all over 0.05. That's 13.863. So let's say this is 13.863 in terms of years. So this will be our answer and solution for the second question. So question at B. Okay, so this will be our solution for this first example. Okay, so let's have this second example. A bacteria culture is known to grow at a rate proportional to the present amount. After 1 hour, 1,000 strands of the bacteria are observed in the culture, and after 4 hours, 3,000 strands are required. Find the approximate number of strands of bacteria originally in the culture. So we are looking for the amount of bacteria or the number of strands of bacteria that is at time is equal to 0, or that is n of 0 is equal to. Okay, we are required to determine that value. Okay, we have this two sets of given. We have that is at time is equal to 1 hour. Okay, the time is equal to 1 hour. We have the amount of bacteria, that is n of 1 is now equal to 1,000 strands. Okay, then the other set, that is at time is equal to 4 hours. Okay, the amount of bacteria, that is n of 4, is now equal to 3,000 strands. Okay, we are to use these two sets. So from our equation, the number of population at time t so equal to the c e raised to k times t. So we don't have yet the constant c. So first we are to compute for that value. So let us use the first set. That is at n equal at n of 1, that is 1,000, or that is at time is equal to 1 hour. So we are just to substitute, that is 1,000 is now equal to, again I'm using this equation, 1,000 is equal to c, this is e raised to k, multiplied by 1. So simply, our equation number 1 is 1,000 equal to c e raised to k. So for example, let us compute the equivalent of this term. This is e raised to k. What will be its equivalent? That is simply e raised to k is simply equal to 1,000 divided by c. So let us use the second set of given. At time is equal to 4 hours. N of 4, that is equal to 3,000. So again, we are using this equation. At n of 4, 3,000. So this is, we have 3,000 is equal to c. This is e raised to k. The time now is 4. So we'll be having this equation, our second equation, as so 3,000 equal to c, e raised to 4 times k. So we have the equivalent of e raised to k from our first equation, that is equal to 1,000 over c. How do we simplify this term, the e raised to 4 times k? So we can have it as 3,000 equal to c. E raised to 4k is the same as e raised to k, e raised to k, I raised to 4. Okay, so from our algebra. Okay, so let us now substitute. What is the equivalent of e raised to k from our first equation? That is simply 3,000 equal to c. The equivalent of e raised to k from our first equation. That is the same as the 1,000 divided by c, and this is now raised to 4. So we simplify to compute for the value of the constant c. We may cancel one of the c. This is now 3,000 equal to 1,000 raised to 1,000 raised to 4. We cancel one of the c. This is now divided by c raised to 3. So if we are to compute for the value of c, this is c raised to 3 by cross multiplication. ay 1,000 raised to 4 divided by 3,000. So this is now raised to 1/3 or cube root. Okay, for us to determine the value of C. So computing for the value of C is equal to this is 1,000 raised to 4 divided by 3,000 raised to cube root or raised to 1/3. Okay, so let's say this is 693.361. Okay, that will be the value of the C. Since we have now the value of C, we can now compute for the value of the K. So from our first equation, e raised to K is equal to 1,000 divided by C. E raised to K is now equal to 1,000. The computed value of C is 693.361. So let's check. So 693.361. So how do we compute for the value of K? We are using again ln. This is ln of E raised to K is equal to ln of 1,000 divided by 693.361. So we may now bring down this exponent, okay, the K. Okay, then multiplied by the ln of E is equal to the ln of 1,000 divided by 693.361. So what is the equivalent of ln of E? That's the same as 1. So let's have our proportionality constant, K. That is the ln of 1,000 divided by 693.361. That is 0.366. 0.366. So we have now the value of C and the value of K. Again, we are looking for the original number or the original amount of bacteria in the culture. That is at time is equal to 0, what will be the amount of bacteria? N of 0. So from our equation, that is the N of T is equal to C e raised to the K times T. So this time we are now to substitute. So this is at N of 0 is equal to C. What is the value of C? Computed value is 693.361. This is e raised to K. What is the value of K earlier? That's 0.366. Raised to 0.366 at time is equal to 0. But basically, again, any number or any value raised to 0 is the same as 1. So we have the amount of bacteria originally, that is time equal to 0, is 693.361. Or we may round this up, let's say 694. So there are 694 strands of bacteria originally in the culture. This will be our solution for problem number 2.